Hi everyone, welcome to lecture 22. And today we're going to talk about zero knowledge proofs, extending a little bit of what we learned from the hardness of approximation. So we're going to use that idea of proofs again to see how we can tell people that we know stuff without telling them how we know it. Okay, so all right. And the lecture today is divided into two parts. So we're going to begin with the administrivia, and then we're going to tell you why you should care about zero knowledge, and then we're going to talk about formally zero knowledge proofs. Okay, so please rate the course. Like, this is great feedback for me and for the school. And now I'll give you like 5 to 10 minutes to do it, and we'll come back after that. All right, so now that all of you evaluated the course, we can keep going. And all right, so another thing I wanted to talk about before starting is research opportunities at the University of Waterloo. So, for those of you who, would like to try your hands after research because you're enjoying your final project work, or just because you wanted to try something different before you graduate, or because some of you are interested in grad school, which is excellent. You should consider doing either URA, URF, or USRA with some faculty at Waterloo, and you can see research openings on these links that you'll have access to. And also, you can always ask a faculty that you really like if they have open opportunities for research, or you can look at the web pages. Okay, so I highly encourage you to do some research opportunity, because in this class, I wanted to give you some of that opportunity, and if you enjoy, you can take it further. Okay, so all right, so now let's start. Why zero knowledge, right? So in cryptography, we want to communicate with other people, with other entities whom we may not trust, right? So we're assuming that we don't trust most entities out there. And now, even if you say, well, what if I do trust the other entity that I'm communicating with, but what you may not trust is actually the channel of communication, right? Because someone may eavesdrop your messages, or messages could be corrupted, or someone might try to impersonate us, right? So it's a really wild world out there. So then, like, all these possibilities can happen, that even though you're talking to someone that you trust, you don't even know if that someone is actually the person or the entity that you think you're talking to, right? So, all right, so here's the situation, for example, right? So let's say that Alice has all of her files encrypted in a public database, but they're encrypted. And then Bob requests from her the contents of one of her files, okay? So Bob is requesting from Alice the contents of one of her files. And she could just simply send the decrypted file to Bob, correct? But here's the thing. Here's one thing that already starts, right? Like, Bob has actually no way of knowing that this message comes from Alice, or that is indeed the right file, right? So here, Bob has no way of knowing, right? Because all he's going to receive is like, oh, here's the file you requested. But it could be someone impersonating Alice, for example, right? So, and since Alice's database is encrypted, there's no way that Bob can know, oh, is this the right message, right? So now, what Alice could do is Alice could prove to Bob that this is the correct file, for example, by sending her encryption key, right? But now, if she sends the encryption key, what happens? In this case, Bob has access to her entire database, right? Because now Bob knows the secret key, Alice's secret key. So that's definitely not a great way of convincing Bob that this is the right file, right? So the question here is, can Alice convince Bob that she gave Bob the right file without giving any more knowledge beyond the knowledge that she gave the right file? Okay, so that's the question that we're interested in. Does the question make sense to everybody? Okay, so, all right, so, and in zero knowledge proofs, we're going to do exactly that. Okay, so what we're going to do here is we're going to give proofs in which the verifier will gain no knowledge beyond the validity of the assertion that's being proved. Okay, so in other words, like, how do you show, right? So let me put it here in English, like, how do we prove? Let's say that you know something without showing how you know it. Okay, so this is kind of another setting. Okay, so all right, so then but before we start, like, getting into the math, this is something that requires a little bit more thought from us, right? Which is the difference between knowledge and information, because here I just said this word knowledge, and you can ask, well, what do you mean by knowledge, and what does it mean to learn something, to gain knowledge, and what is the difference between knowledge and information, right? So let's talk a little bit about this. So the first question is certainly quite complex. So, and it has a philosophical kind of side to it, which makes it very complex and kind of out of scope of our domain here, which is computer science. So let's only talk about the second and the third, which you can formulate based on the intuition that you already have of what knowledge is. Even without kind of having a formal definition of knowledge, we all have a certain sense of what knowledge is, right? So let's use that sense to answer the second and third questions. So here's the thing, knowledge is something that has to do with your computational ability, okay? And in which sense does it have to do with your computational ability? Well, here's the thing, if you could have found an answer, right? And what do I mean by found an answer is that you can always compute it, right? That's how you find answers. Whatever process you use to find an answer to a question, right, is a computational process. You're following certain steps and you're performing kind of certain computations, right? So if you could have found an answer to your question without help, then you gain no knowledge, because you would say, I already know it, right? So for example, if I told you, oh, 2 + 2 is 4, then you definitely know it already. So like, okay, I gain no knowledge from you telling me that, right? So here's an example, right? So if Bob asks Alice whether a graph G is Eulerian, right? So Bob, and Alice responds to Bob, well, Bob gains no knowledge in this interaction because he could have computed it himself, right? And why would he do that? Well, by Euler's theorem, right? A graph is Eulerian if and only if all vertices have even degree, right? So this is something that's very easy to check. So Bob could just have checked it, and by Euler's theorem, he knows that the graph is Eulerian or not. So he didn't gain any knowledge because he could have done it by himself, right? That's the kind of thing that you gain no knowledge, right? But now, for example, if Bob asks Alice if a graph G has a Hamiltonian cycle, that's a much different question, right? Because now, Bob upon Alice's response, let's assume that the response is correct, now Bob gains knowledge. Because if P is not equal to NP, Bob cannot compute it. Does that make sense? So this is how one is gaining knowledge, right? And I mean, and this is just something that we're saying oh, it's either P or NP, just because we're computationally speaking, right? But even if you think about it in terms of whatever computational model we are as humans, right? Like for example, there was the computational model of you being a student prior to CS 466, and you probably didn't have a lot of computational power or a lot of knowledge of a bunch of topics that we talked about in this class. But now post CS 466, you're much stronger computational model, because now you know all these really cool facts that you learn in all these lectures, right? So you become a more powerful computational device in the world because you know more, right? So, and this is what knowledge has to do with, right? It has to do with our computational ability, right? Because now, for example, if we talk about any of the topics that we talked about before in class, and I give you an exercise like, oh, I know how to solve this. And why do you say you know how to solve it? Is exactly because now it's within your computational ability, right? So does that make sense? So this is kind of our intuition of knowledge, right? So let's just use this intuition to talk about this. Now, let's talk about the third question, the third bullet, right? So the second bullet, we know now, oh, to learn something, to gain knowledge means to become kind of more powerful, like computationally, or like to access something that we could not compute, right? But if you notice, in both cases of the examples here that I gave, Alice conveyed information because there's a graph there, and then you ask, is this Eulerian? And then there's an extra bit of information that you extract out of it, right? In both of the examples. It's just that one you could have computed yourself and the other one you didn't. Does that make sense? But in both cases, information was conveyed. Now, what does it mean, right? So let's try to kind of distill this discussion that we had. Well, knowledge here is related to computational difficulty somehow, right? And is also about publicly known objects. What are the public known objects? Well, is the graph that Bob is asking Alice about, right? And there's some problem about this graph that, given its computational difficulty, will either tell us whether we gained knowledge or we didn't, right? And the idea is one gains knowledge when one obtains something one could not compute before by themselves, right? So that's the idea of knowledge that we're going to use, whatever the word means, right? And information is unrelated, is completely unrelated to computational difficulty. And it's only about partially known objects, right? And one gains information when one obtains something one could not access before, right? So, and here is kind of, you know, what we had is like, okay, there's a graph and there's like, is this, and the question, but the answer was not there, right? Even if we can compute the answer or not, the answer was not publicly there. So then once we give the answer, we're conveying information, right? So now there's more information afterwards. Does that make sense? So that's kind of the difference that we're working with here. Okay. So, all right. So now that we know a little bit about knowledge, and the knowledge has to do with computation, whatever that means, whatever the word means, now we can talk about computational complexity and algorithms, right? Because now it's within the realm of algorithms, or whatever I can compute, I will gain no knowledge, right? So, okay. So now let's talk about the classical proofs again, right? Like, so hence the knowledge from the previous lecture. So what is our usual notion of proof, right? A claim, someone gives you a claim, let's say a graph is Hamiltonian, and a prover will write down a proof that C is correct, that this claim C is correct. And then the prover can send this proof to a verifier, and then the verifier has a procedure, right? And the procedure is like axioms and derivation rules, like, which is like the logical rules that we have to check the validity of the proof, right? And the verifier accepts or rejects based on these rules, right? And if you think about NP, the way that we defined NP in a couple of lectures ago, this is exactly kind of the realm of NP in the way that, you know, if you give me a claim, I give you a short proof. If a claim has a short proof, if it's correct, then we're in the NP realm, right? So, all right. But then what is the difference here, right? So one, this is one-way communication, right? So there's very little interaction going on, because here only there's a claim and a prover is just sending you a proof, right? So, all right. And here, what is the other thing that we need to realize is that the verifier, remember, does not trust the prover. Otherwise, there's no need to verify the proof, right? Like if you really trusted everything I said and never read the lecture notes, you just say, well, whatever Rafael is saying is true. I'm not even going to mathematically check if I understand it, right? Like it is all correct. So there's no need to verify it. But that's the whole point, that we don't trust the prover or the proof that we're given. We need to validate it. We need to verify it, right? So, all right. So again, let's just talk about NP just to kind of rehash the same example, right? Like a claim that X is in the language is given, and then a prover will just write down a proof, like a witness, that X is in the language. The prover will send the witness to the verifier, and the verifier has a procedure, like it's axioms of derivation rules, to check the validity of the proof. In the case of NP, we have deterministic polynomial time algorithms, right? And the verifier accepts if and only if this verification process returned like 1 or yes, right? And in this setting, here's the thing, the verifier learns the proof, right? Because now, for example, we know that C could be, the claim C here could be like graph G, like a certain graph G is Hamiltonian, right? That would be the axis in the language, right? G is in the language of the Hamiltonian graphs, right? And then the prover would just say, okay, here's the proof. Like I give you, like the prover gives Hamiltonian cycle. Right? And now what happens? The verifier will learn this proof because the verifier has access to the cycle. Does that make sense? Now the question is, how could we prove something without conveying the cycle, right? Without conveying this information, right? Here's another one that you know, right? So factoring is another very famous one. So a claim that n is the product of two primes is given, then what happens? A prover will write down a proof. What is the proof? Just two primes P and Q, such that n is the product of these primes. And then the prover will just send P and Q to the verifier. And what does the verifier need to do? The verifier just need to check the validity of proof, just computes P and Q and checks that both of them are prime and checks whether P and Q is equal to n, right? So again, this is a deterministic polynomial time algorithm, right? So we know that factoring is in NP, right? All right. So, and that's what we said, like the verifier accepts if and only if P and Q are prime and the product is equal to n. Now, again, in this setting, the verifier is learning the proof. In this case, like the factorization of n, right? So we're conveying this information because, well, we don't know how to factor, right? Like let's say that we are classical Turing machines. So we definitely don't know how to factor fast, like not yet. But the thing is, then in this case, we actually gain knowledge because knowing this is something that was outside of our computational ability, right? Like according to current assumptions. Does that make sense? So far so good? Okay, so, all right. So then, now let's talk about graph isomorphism, right? So what is the graph isomorphism problem? So here's the setup. We have a claim C that graphs G0 and G1 are isomorphic. And what does it mean to be isomorphic? Okay, let's talk about this problem. So two graphs are isomorphic if and only if there is a permutation of the vertices. Okay, and this permutation, I'm gonna say like sigma, that maps the vertices of, G0 to the vertices of G1. To the vertices of G1. Okay, so they have to be the same number of vertices, of course, right? Such that if you, like U and V, they are an edge of the first graph, if and only if sigma U, sigma V is an edge of the second graph. Does that make sense? So is if I permute the vertices, then the edges also get matched, right? Like this permutation of the vertices kind of is compatible with the edges, then we say that the graphs are isomorphic. Does that make sense? So let me just give you an example here. So let's say that we have the graph like 1, 2, 3, and then we have the graph right? You can just say 1, 2, 3. So then here, what is the permutation? If my permutation sends, let's see, 1 to 1, sends 2 to 3, and sends 3 to 2, what do I have? Is this an isomorphism? Let's see. Well, so 1, 2 will become 1, 3, right? So this vertex is good. like this edge is good, like it gets sent to this, and 2, 3 gets still sent to 2, 3, so this also is good, right? So these graphs are isomorphic. Does that make sense? And this sigma is an isomorphism. And of course, like if you see this simple example, so obviously they must be the same graph because it's kind of up to labeling. And that's exactly what this kind of graph isomorphism is trying to say, right? It's just that here I gave you a very simple object, but you can clearly see that when graphs become much bigger, then this problem tends to be hard, right? So, okay, it's quite a, all right. So now what happens, right? So we know what the graph isomorphism problem is, and now a prover will write down an isomorphism such that the isomorphism rho from rho is the same as sigma here. Okay, I could have written sigma. I wrote, but rho is the same. Is the isomorphism such that rho of G0 is equal to G1, right? And now the prover could send rho to the verifier, and now all the verifier needs to do is to check that rho is a permutation of the vertices. That's the first thing. And that like all the edges, like they get, like for every edge that's in the graph here, we have a new edge. And every edge that's in G1 has a pre-image, right? Like from an edge of G0. Does that make sense? Through the permutation, right? Because we have the if and only if. Okay? So, okay, again, that's easy, right? And the verifier accepts if and only if the above is correct. But now, here's the thing. Again, in this setting, the verifier has learned the isomorphism, like it learned the proof. So somehow, in our classical way of proving that we know something, we actually reveal the entire proof, right? And remember, this is no good for Alice that she's trying to prove that her unencrypted file is exactly the same as her encrypted file, because now if Bob had to know the secret key, then that's really bad for her, right? So, all right. So can we convince people differently, right? That's the idea. Can we convince a verifier differently? And the answer is yes, but now we need to modify the way proofs are checked. And remember, we already saw one way that modification could happen is that without having a deterministic algorithm, we could have a probabilistic verifier. And then the verifier doesn't even need to look at all the proof, right? And that was the PCP theorem that we saw before in the hardness of approximation session. Now, but here's we're going to modify it in a little bit different way. But again, we're going to have the same class that we had before, which is the interactive proofs. What we're going to do now is, again, we're going to make the proofs interactive instead of only one way. So now there's going to be more communication between the prover and verifier. And this gives us more power. Right? So now, for example, the verifier is allowed private randomness. And what do I mean by private randomness here? Is randomness that the prover is not aware of. The prover cannot see that randomness. So you can flip coins without me looking at them. Does that make sense? Because if I knew, that doesn't count as randomness. If I already knew all the coins that you're going to flip and how you flip them, then that would be no good to me. No good to you, right? So, all right. So, and in the end, so what are we going to see in the second half of the lecture? We're going to see a zero knowledge proof for graph isomorphism. Okay. So Alice is going to tell Bob, okay, so I will not give you an isomorphism, but I will prove to you that I could give you one if I wanted to. And that's how you can prove that the graphs are isomorphic, right? Because if the graphs are isomorphic, there is an isomorphism. And all that Alice says is, well, so here's the idea, right? So we have the graphs G0 and G1, they're isomorphic. So if they're isomorphic, there is some isomorphism rho, right? Like this is the isomorphism. But Alice does not want to reveal rho. So what she's going to say is, well, I'm not going to give you rho, but I'll prove to you that I could give you one if I wanted to. Does that make sense? So, okay. So we're going to see that in the second half, okay? So, and this is like the motivation for this coming half. Do you have any questions so far?